everyone to this HFIP spatial seminar. And I wanna let everybody know that this meeting is being recorded. And if you wish not to be recorded, please turn off your camera, and then you can ask questions through chat. That way you will not be recorded in the recording. So with that, I would like to request Frank to introduce our speaker for today, Dr. Kerry Manuel. Frank, go ahead.
Yeah, thank you. It's my pleasure. I've known Kerry probably 45 years, old friends and classmates. Dr. Kerry Manuel is the Cecil and Ida Green Professor of Atmospheric Sciences, the Department of Earth and Atmospheric and Planetary Sciences, MIT, my alma mater and his. He is co-founder of the MIT Lorentz Center, a climate think tank which fosters creative approaches to learning how climate works. His research interests focus on tropical meteorology and climate with a specialty in hurricane physics. His interests also include cumulus clouds, the role of clouds, water vapor and upper ocean mixing, and the regulation of climate, and advanced methods of sampling the atmosphere to aid numerical weather prediction. He was elected as a member of the U.S. National Academy of Sciences in 2007, a member of the American Philosophical Society in 2019, and a fellow member of the Royal Society in 2020. He was named one of the Time 100 Influential People of 2006. Kerry received his BS and PhD from EAPS at MIT and PhD in 1978. With that, Kerry, please go ahead. Thank you so much for joining us.
Well, thank you, Frank. It's really great to see you. I wish we could see you in person, but I hope that day is coming soon. And I see a lot of familiar faces of friends and colleagues. So delighted to be with you. Just because I work at an institution of technology doesn't mean I know how to use technology. And I'm afraid I've never used this Google Meets to share a screen, but I will try to do it now. See if I can get that to work. How is that working for you? Do you see this in full screen?
It's
Yes.
coming up. Yeah, we got it now, Kerry.
Yes.
Okay, great. Okay, terrific. Well, I wanted to talk to you today about work I've been doing as part of the HFIP effort with my graduate student, Jonathan Lin, who's done almost all the work I'm going to present today, and also with Jonathan Vai at NCAR, who is working very hard to get this out to the public as in terms of real-time forecasting. So just to sort of orient everyone, this will be old news to forecasters and so forth, is that we talk about traditional hurricane forecast metrics as track and intensity, okay? And of course, there are all kinds of variations on this, but all of the emphasis ever since we started doing forecasts understandably has been to try to forecast the track and try to forecast the intensity of the storm. And our measures of how skillful we are also based on that. We have track error, we have intensity error. But there's a problem, I would argue, and some of my colleagues, with this dichotomy. And one of the problems is that gets people tangled up a little bit is that when we talk about the intensity, usually we mean the maximum surface winds within the storm, but hurricane force winds can occur far, of course, from the center of the storm, and so this presents a communications problem. But the big item here is this point that the intensity errors are not independent of the track errors. In fact, I'm going to show you some research that suggests that, again, this may be old news, the track errors at longer lead times, the major source of intensity error. So when you try to use them as independent metrics of skill, you can get into trouble. And we think that the solution to this problem, or a solution, is to migrate away from this track intensity dichotomy and try to focus on what we call pointwise wind probabilities. That is, probabilities of hazardous conditions, wind being one of them, at geographical locations where people live. we're already doing that. NHC is already doing that. It's just a question of also doing that in terms of skill evaluation and maybe moving the emphasis away from track and intensity to this pointwise probabilistic forecasts. And that also presents obviously some communication challenges, but I'm going to try to argue that we should try harder to get to that point. Now, I want to just sort of say that this is almost natural to the public when you get away from hurricane forecasting. If you are talking about a winter storm here in Maine, where I'm sitting at the moment, we often, I mean, weather forecasters will talk about the track of the cyclone, but people basically are just going to turn on the radio and ask, is it going to snow? When's it going to start? How hard it's going to snow? How hard will the wind blow? And they're not really thinking very much in terms of tracks and intensities of extratropical cyclones. I suppose it seems a bit more obvious in that arena, but I suggest we try to move in the direction that we're already doing for extratropical cyclones. As I mentioned, the Hurricane Center has been doing this for a while. And here is a map of hurricane force wind probabilities, forecast from not so long ago. Okay. The other problem, though, which we have tried to address in our own work, is that even in this case, the probabilities have been mostly generated from climatological statistics. That is, they're not state-specific uncertainties. They're sort of climatological uncertainties. And can we make these more state-specific? And the solution is to go, of course, to Ensemble Forecasts, which is what this is all about. Well, let me take a little bit of a detour here. And again, this may seem somewhat obvious to you, but there may be some things coming on that aren't quite so obvious. Is why are ensembles necessary in the first place? Is because uncertainty will always be with us, no matter how hard we try. And that raises the question, which is the source of this little detour, is what are the fundamental limits on tropical cyclone predictability? By fundamental limits, I mean the Lorentzian type predictability limits. What's the limiting time horizon as you make models and observations perfect in that limit? And there is apparently a limiting time horizon for weather forecasts of all kinds. So we're going to take a stab at estimating what those time horizons are. And to do this, we're going to do a bunch of experiments generating very large numbers of tropical cyclone tracks with a risk model that we've developed over the last 15 years at MIT. Some of you are familiar with. This is a sort of MIT synthetic track model. I'm not going to go into great details about this, just a little bit. So for the control experiments for each of these things, we begin with climatological quantities, potential intensity, mid-level humidity, daily winds. We, in this case, take this from NCAR-NCEP reanalyses. We take those time evolving states and seed them randomly around the world. And those seeds move according to a beta and advection model. And then we run the CHIPS intensity model along each track. Now, of course, needless to say, none of these components is perfect. But what we're trying to do here, obviously, is not to make forecasts, but to do what's called perfect model experiments, where you have a reasonably good model, you regard that as the truth, and then you see what happens if you start introducing errors, like in the initial condition. So we'll get to that in a minute. In practice, only a small fraction of the seeds that we put down magnify to tropical storm strength or greater, and we throw away the rest. So we call this genesis by natural selection, and it works. Surprisingly, when I first tried doing this 15 or 16 years ago, I had no real faith that it would work. It's still kind of interesting to me that it does. So for this exercise, we generated 3,500 storms between, again, from the reanalyses between 1980 and 2014. Once we have those 3,500 storms, we go back and reforecast all of them. in exactly the same conditions except for perturbations. So for each storm, we perturb in one set of experiments the initial intensity by increasing or introducing a positive 3-knot error. We introduce perturbations to the environmental shear, environmental winds, by allowing the large-scale flow to decorrelate from the control over 25 days. By 25 days, it's just as different from the so-called truth as any random selection of flows from that time of year. And we do another experiment where we perturb both of them. Another set of experiments where we allow these decorrelated winds to affect the track of the storm, not just the intensity. And then we do that, so all kinds of possible combinations. When we do this perturbations, there are some tracks that don't make it through our natural selection algorithm, and we have to throw them away. And so we don't have 3,500 overlapping cases, and this table shows the number of overlapping cases that the storm exists in both the control and the perturbed experiment. It's also a list of basically a summary of what I just said. This is published in a paper I wrote in 2017 with Fuxing Zhang. Let's just look at the track errors first from this approach. So this again is done by, when we do this perturbation experiment, everything is identical to the control except that we allow the large scale winds to decorrelate smoothly from the control over 25 days, which is extremely optimistic. It's saying you can predict the large scale very well with a time horizon, a predictability horizon of 25 days, which is somewhat longer than what we can actually do today. But there's some hope that we can get that far out in large scale wind forecasts. That's why I use 25 days. So this is the mean absolute track error of these 2,000 to 3,000 overlapping events that allow us to calculate that. And then the red dots are the NHC Atlantic track errors from, accumulated from 2000 to 2015. So the difference between the red dots and the blue is an estimate of the difference between what we're actually doing and, in a perfect world, what we could be doing, if you will, in an almost perfect world. So it's nice to know there's some room left for track improvement. Tracks, of course, have improved, track forecasts have improved greatly, but this suggests that, yeah, we could still do better, and that's nice to know. This is the same thing for intensity, and there's a lot on this slide. I don't want to belabor it, but we're again looking at the RMS difference between the control and perturbation. And let me draw your attention first to this dark blue line at the bottom. It's the RMS error when the only difference between the perturbation and the controls is 3-knot initial intensity error. And that's where you see the 3 knots down here at this end. And it increases and it saturates at 4 days or so. And you might be surprised, well, why does it saturate? And the simple reason is that a lot of storms start decaying or are gone by 4 or 5 days. And so you have to be careful about when you shut off this comparison. Obviously, if you carry it to 0, you can always make a perfect 40-day forecast of a hurricane. That perfect forecast is that it won't exist. Okay, so this is why these errors tend to saturate here. It's because as you go out this curve, and I have a graph that shows it, although I didn't include in this presentation, the number of storms keeps dropping. The red curve is starting from 0 initial error, but we're allowing the shear as it affects the storm intensity to decorrelate over 25 days. And that catches up to the initial condition error only in about 4 days, but then gets somewhat larger over time. The yellow is if you have both initial intensity errors and shear decorrelation. And then the purple curve is allowing no perturbations to anything except the track. That is, we're letting the environmental wind decorrelation affect the track, But the shear we feed into the intensity model is the same shear we fed into the control. It's a little bit kind of hypothetical. Obviously, in reality, it would be moving into an environment of different shear that should affect the intensity. But we just did that. And so you can see that by day 4, this catches up to everything else and becomes the dominant source of error. This is simply saying that after 3 or 4 days, the track errors are the main contribution to intensity errors. The storm is just moving into a different thermodynamic environment and kinematic environment in reality. I didn't really talk about this, but later we started perturbing the mid-tropospheric moisture anomaly in the core of the storm at the initial condition. That makes a huge effect, but it saturates very quickly. And we haven't done combinations of inner core moisture and other variables. The black curve is the NHC error as a function of lead time from 2009 to 2015. And here again, it wouldn't surprise anybody to know that we have some distance to go, right, till we get to sort of idealized conditions for that. So this is all a bit of a detour to say, yeah, I mean, uncertainty is not only matters, but we'll always have uncertainty, even if we can drive things down to these fairly hypothetically perfect scenarios. And of course, forecasting skill has, as you all know, been improving, especially with tracks, rather dramatically over a period. We haven't been forecasting intensity or scoring it as long, but there has also been improvement in intensity. The interesting thing is that it's not easy to rule out the hypothesis that all the improvement in the intensity forecast was a byproduct of improving the track forecast. And this is another problem with the fact that the two are obviously not independent. So it's not, I'm not saying that the improvement in the intensity is entirely because we improved the track. All I'm saying is it's very difficult to rule that out without doing a lot more work. Okay. So the situation for intensity may be worse than we think it is in some sense if we're just improving intensity as a product of improving track. And I would say that in some sense, this dependence of intensity error on track errors is a big impediment to progress in hurricane forecasting. And I am advocating, and I expect pushback on this, but you know I've never been afraid of that because I think it's these discussions. But I think we need to do a serious reevaluation of what we are using for skill metrics. Mostly because of this lack of independence. So I'm advocating moving away from metric to people-centric metric. And by that, things like hazards at specific locations. I think we're already moving in that direction, but I think we should be moving a little bit faster. Basically, I'm saying unless you're a captain of a ship at sea, which is a bit of a special case, or the crew of a ship at sea, what you're really interested in are what's going to happen where you are, right? When, what, and how probable. And doing this is not just a question of scientists and forecasters doing it, but a question of educating the public into interpreting these kinds of metrics. I won't talk to that because that's really a specialty for social scientists. But I would argue that moving to these would help also redirect attention to improving forecasts that matter to people. So this is kind of a strange thing to say in a way. I mean, we're all meteorologists and we're focused on things like storms, and that's just as it should be. But maybe we ought to reconsider what it is that should be important to the users of the information we're producing. And I would argue that conditions at points are probably more important to most people, including people like emergency managers, and maybe we should focus more on that. So let me give you, this is just by way of starting a conversation more than anything else, Let's suppose that by way of comparing these track-centric metrics to people-centric metrics, supposing we're interested in some arbitrary place that happens to be in North Carolina, where that red star is. And let's say in the first instance that there's a forecast of a storm that will pass just to the south of this place and affect it somehow, all right? But let's say in reality, the storm does this. It's a fairly large forecast error, but this is just a sketch. It's not an actual forecast. And let's also say that the storm actually rapidly intensifies by some metric somewhere along the way. Okay. So that being the case, when we rack up our intensity metrics, this event is going to give you a very large error because the intensity here, when the storm was, say, 72 hours away from national is, let's say, much more intense than it was here. Whereas any ensemble member that went anywhere near this place under these meteorological conditions really didn't have any chance of rapid intensification, let's say. So the probabilistic forecasts for this place, including after you score them, might be perfectly fine, hypothetically, but the storm-centric metrics could be terrible, right? So in some sense, in this case, doing storm-centric intensity errors as penalizing us unnecessarily. Because the other thing I would say is that if it did take this, essentially it doesn't affect the person here. And this eventuality may in any case been part of some ensemble. So we have a spectacular storm-centric 72-hour forecast error, but if we had a good probabilistic intensity forecast, and this is made up, obviously, for this town, I'm calling it our town in North Carolina, you know, maybe the actual reality was somewhere within this fairly high probability envelope. Or it was out here, okay, if the storm went off and rapidly intensified, sorry, it's out here, but it produced hardly any wind in any case at the place that we're interested in. So let's just pretend, and this is made up too, that over a long period of making forecasts for this town, we compare the probability that we forecasted it to the number of cases that verified. So we get a so-called reliability diagram. And if things are along this diagonal, they're probabilistically very good forecasts. And if the reality is pretty close to this line, we could say, we're doing a pretty good job forecasting for this town. And of course, we would accumulate that over many, many places. Maybe a grid of places, maybe populous places, whatever, but probably not over the ocean. And so what I'm saying is that we could turn out to be making what statisticians and meteorologists would agree are pretty good probabilistic forecasts for this point, even if we have some amazing forecast busts from the point of view of traditional intensity metrics. And it's because the intensity bust is associated with a track bust. And I would also argue things that maybe the timing of rapid intensification becomes less of an issue for pointwise probabilities than for storm-centric evaluations. So going back to my little map, you know, if you rack up traditional intensity metrics, if you have rapid intensification and you forecast it perfectly, but with a 12-hour time error, and you do your classical RMS intensity, you're going to get a big, big error. But if the intensification occurs 1 day out versus 2 days out along this track, if we pretend it intensifies along this track, it may not make that much difference for the conditions at this point. It might, but it might not. And so maybe the timing of it isn't quite so important for these probabilistic forecasts. Speaking of rapid intensification, I was asked to say something about this, and some of you have heard me say this. Formally, there isn't any such thing. It doesn't exist. There is no such thing as rapid intensification, except as we've defined it into existence. And this is important to me, but I want to make this point. This has been done over and over again with models, with data. If you just take a long history of hurricanes, real ones, model hurricanes. They all do the same thing pretty much. And you just do a histogram or a probability diagram of intensification rates. This is in knots per hour with 0 in the center. So we are also including dissipation, not just intensification. And this is the log of the probability here. You get this almost perfectly logged exponential distribution. All right. The blue is from best track data in the Atlantic. The red is from the synthetic tracks that we generated at MIT. The green is just the expected sampling error. So if the blue curve falls within the green curves, you can't statistically distinguish it from the red curve, but never mind. There are no breaks in these distributions anywhere. Okay, there's no phenomenon of rapid intensification in nature. There's just a continuum. And I can't emphasize that enough. We've defined it into existence, and I wonder whether we should have. Okay, and I'm wondering whether we should take it back. For one thing, introducing any arbitrary threshold into a verification metric can lead to artificially inflated error estimates. So if you have a binary, it rapidly intensified or it didn't, and it's 30 knots in 24 hours, and you forecast 29, and it was 35, you got a miss. If you forecast 80, you got a hit. Does that make any sense? I'm exaggerating only a little bit. It doesn't matter so much if your metric is the pointwise probabilities. It may show up in there depending on whether it's just a timing error or whether it's something else, but it's part of a continuum. Why introduce thresholds? I'm sort of opposed to thresholds, I guess, and I think I'd like to start a discussion on whether we really should be backing off on this fascination with so-called rapid intensification. In my view, it's morphed from a formal thing for the convenience or effectiveness of forecasts into a kind of almost subliminal thinking in terms of researchers that there's a real thing there. There isn't a real thing there. It's not real. It's defined into existence, and I'm not sure it's helpful for forecasts. Let's discuss it. As you know, I like to be provocative, but I do think that we need to reconsider this. All right, so now let's get right into the meat of this, which is ensemble forecasts. And that's the future of weather forecasting, including tropical cyclones, but we aren't really quite there yet. So this is an ensemble forecast from the European Center, 51 members for Hurricane Irma back in 2017. And you can see the actual track in red and these ensemble members in black. But there's a problem with this. And they're computationally expensive, running all these ensemble members, and they have somewhat lower resolutions, typically, than the operational or deterministic model. And even in the case of the European Center, those resolutions are inadequate, really, to resolve the core of tropical cyclones today. And so we get a big negative bias in intensity. So this is one forecast. It's Irma. This is what happened. These are the ensemble members. Forget about it, right? I don't think anybody takes that seriously yet for these ensembles. So we can't quite do that. This is in addition to the fact that 51 ensemble members really isn't enough. Okay, so we tried to get around that, and this is the work again of my graduate student, Jonathan Lin, to try to do a better job and to work toward a state-dependent forecast uncertainty using ensemble numerical weather prediction systems. And we do that by generating a much larger ensemble, say about 1,000 members seems to be close to optimal, from one of the global forecast models' more limited ensembles, like the GFS ensemble or the European ensemble. And so we're trying to generate large ensembles of tracks and intensity and get things like exceedance probabilities from that. And we have done this in hindcast mode for every hurricane in the Atlantic and Eastern Pacific. twice a day from 2015 to 2018 inclusive. And I'm just going to tell you a little bit about how we do this. We start with the global forecast model ensemble, the GFS or the European ensemble. We derive from that certain environmental quantities. And then we use the covariances of the actual track displacements from the global model to generate synthetic tracks that have the same covariances. And once we have those, the 1,000 tracks, kind of bootstrapped up, if you will, from the global model ensemble, we run an intensity model along each of those tracks. We fit a canonical surface wind distribution to that, and then we have our 1,000-member ensemble. It's pretty fast, fortunately. We can sort of do this on a desktop computer. We don't have to call the power company before we do this. So the tracks in this thing are determined largely by the large-scale steering flow. And what we do is use the translational speed covariance from the tracks from the global model ensemble to generate synthetic displacements. It's really very simple and pretty robust. So we start with these 51 or whatever we have ensemble members and bootstrap up to 1,000. I'm not showing you 1,000 ensemble members here, but I'm showing you the track density over a quarter-degree grid of that 1,000-member ensemble from a particular forecast. Okay, this is what the red curve is what the storm actually did. So this is, I think, fairly robust, easy, not very controversial. It's just statistical bootstrapping of an ensemble of tracks. I've said nothing about intensity yet. Here is just another rendition of this is the 50-kilometer strike probability. That is the probability that one of these events will come within, that the storm will come within 50 kilometers of every point on this map. Okay, from this 1,000-member ensemble. We can look at the mean absolute error of these tracks. And so what I'm showing you here, again, for this period of time, is taking the 1,000-member ensemble and averaging it, get sort of an average track. We do this for European Center bootstrapping, the GFS, and then the mean of the two, basically. And that's the blue curve, these are absolute errors times its initialization, the blue curve, the green curve, and the GFS is the orange curve. And then in this particular case, we actually beat HFIP, but I'm not sure that's very typical. This is the reliability diagram, the probability of storms passing within 50 kilometers of each point, the observed probability over all the storms versus the forecast probability. These same things. We can't do it with HFIP because we don't have the ensemble. So you can make of that what you will, but this is the sort of thing that we would have to strive to improve. Now, what about the intensity? Well, there's several different ways to do that. We did it using something called the FAST system, which is a CHIPS emulator. And it's kind of an interesting thing. It's basically a pair of ordinary differential equations. You can integrate that in a second on your laptop. But let's talk about what the variables. The two variables are the maximum wind speed in the storm, V, and another variable which is not of direct forecast interest, but which is coupled, which is inner core moisture in the free troposphere, little m. And these have been designed, if you will, to mimic the behavior of chips and also to conform to certain expected theoretical limits. Little m cannot be larger than 1. And when it is 1, the maximum wind speed you can have is the potential intensity. So this will never forecast circular winds larger than the potential intensity. And m you can show is bounded between 0 and 1. So we have potential intensity. This is the spin up term. This is a spin down term. This is moistening. This is a ventilation term. That's the potential intensity. S is the magnitude of the environmental shear, which again is going to be coming directly from the large scale ensemble. Not directly, because we have to remove the vortex. I'll come to that in a second. Chi is a measure of how dry the middle troposphere is. This is the so-called ventilation term here. So we run that along each track. And just to show you one example, this is a hindcast of Hurricane Ivan, whose intensity history is this black curve. The hindcast with the CHIPS model is the blue curve, and the hindcast with this FAST model is the red curve. And so they're sort of similar. It does what it's designed to do. It kind of emulates CHIPS. And if we did that for all the storms of the 2004 season and accumulated intensity errors over the lifetime of each of these storms, for the simulator and for CHIPS, sometimes CHIPS does better, sometimes the simulator does better, and it is what it is. But I want to say that we could substitute other kinds of things like the CHIP model itself for this. We just chose to do this because it's fast. So just one technical detail, because the European and GFS ensembles actually usually have the tropical cyclone in them, what we're calling environmental winds for the purpose of steering the storm and for the purpose of shear ventilating the storm, we have to take that vortex out. So we have to do some vortex surgery. How do we define the environment? We do that by first calculating both the vorticity and the divergence, and therefore a stream function and velocity potential, which are much more localized. We remove the high vorticity, high divergence cores, and then we reinvert these equations to get back what we call the environmental wind. Okay, this is done, for example, routinely and has for decades for the ship's model, which also needs to have an environmental shear. Okay, so when what does it look like when that happens? So I'm going to show you the environmental shear, which is a mean shear amongst all the large-scale ensembles. These are the 51 or 26 or whatever it is numbers. And I'm going to play you a movie. These black points are the locations of the European Center, I can't remember which is the European Center or GFS initial vortex, and you can see how the shear spread amongst these ensemble members grows over time, partly because the ensemble variance increases and partly because the storms are moving into different places. In fact, this is just showing how the RMS internal variability changes over time, and generally speaking, as you'd guess, it increases, and that limits the predictability of intensity. Well, I think I'm going to skip the tutorial on ventilation. It's just we basically use the humidity in the environment of the storm. I will show you a little film of ventilation here, just for kicks. This is just showing this chi parameter from reanalysis data for one storm located, and we're in storm coordinates here, the black dot. That went by pretty fast, but you can see dry air wrapping into the core of the system. So this is just a kind of an example of ventilation going on. Then finally, once you have the track and the maximum wind speed, you have to have a wind model that gives you the variations of winds with radius, and we use the one that was developed with Dan Chavas, which is actually theoretically based. It's based on the idea that outside the core, there has to be a balance between radiatively driven subsidence above the boundary layer and Ekman suction at the top of the boundary layer, and that dictates the form of the wind profile. And there's now a fairly extensive literature on this. So now we have all the components, and we can do a sort of pointwise 64 knot, in this case 64 knot wind exceedance probabilities over a very large grid of points from this 1,000-member ensemble. So we run these at 1,000 members. At each point, we calculate the evolution of the wind from this, fitting this radial wind distribution. We actually add on an asymmetric wind component, which we've developed over some years. And it's essentially based on the isobar wind, the fact that there's a response to changing pressure at the surface to calculate the asymmetric wind. There's a great deal of research behind this. I'm hiding in one sentence, but anyway, we get the winds at the surface at each point in a grid as they evolve over time, pick off the maximum over the time evolution and calculate the probabilities. And here are, for 5-day forecasts, the sort of reliability diagrams separately for the Atlantic and East Pacific, and for 3 different exceedance wind speeds, winds exceeding 34, 50, and 64 knots for the different colors. And particularly for 50 knots, we're doing pretty well in terms of probabilistic reliability. Finally, about the future, the model we're using, or algorithm that's attached to that model, can also forecast rain. And here is just one particular track that's downscaled from the European Center, a short track here, and the storm total rainfall in millimeters. This is a rather spectacular one in terms of rainfall because it's stalled. So it's a fairly minor step now to build in probabilistic rainfall predictions. And then downstream, if we couple that to hydrodynamic or hydrological models, we can hope to do some forecasting of freshwater floods. So let me just wrap up because I really wanted this to be more of a discussion. We developed this physics-based probabilistic model to try to quantify the state-dependent uncertainty rather than rely on just a climatological one. And so far, although I think the jury is out because we just need more time to go by, they seem to be fairly reliable probabilistic forecasts. And it turns out that beyond a day or two, it's the large-scale environment that dominates the contribution to the uncertainty, thermodynamic and kinematic environment. And just to repeat what I said at the beginning, I think we need a serious discussion about migrating from these deterministic, storm-centric to probabilistic, people-centric forecasting, including skill metrics. And the including skill metrics is the most important part of that sentence because I think the rest of it's already happening. But I think we need to judge ourselves by how well we do at forecasting at points rather than forecasting the storm. And that may seem a little counterintuitive, but in the future, we want to, we're using, I forgot to say, the intensity model also includes a coupling, which wasn't obvious in the slide I showed, but it is coupled to an ocean, includes a parameterized coupling that's been tested extensively against real coupled models, but it uses a climatological upper ocean thermal structure. Surface temperature, of course, was provided by the ensembles, but the thermal structure is important, and we want to work in real-time ocean. We want to move to generation and verification of precipitation forecasts as well. These wind probability, Jonathan Lin at NCAR is working very hard to include these in what he calls a hurricane risk calculator. So I'll leave you with that, and happy to answer any questions.
Thank you, Kerry. Now I'd like to open to questions. Starting from the chat, there are some comments and questions there. I think the first question, first comment is from James, but the questions is from Frank. Frank, you want to go ahead and ask?
Yeah, so Kerry, first, thanks for a great talk. But there's a number of questions, but I'll start with the first one I asked. Was your introductory work showing the track impact on the intensity forecast suggested a correlation between track and intensity, particularly out at the long lead times? And my question was, is the correlation with the track or with the track spread? And do you know how that correlation works?
Well, I don't, but I can. Let's do a little bit of a thought experiment here. Supposing that I have a storm which looks like it's just going to graze a coastline and then maybe turn out to sea. You can imagine that in that case, a small track error, one that you would normally consider to be perfectly acceptable or normal, could lead to a huge intensity error because it makes a difference between landfall and not landfall. So that makes me hesitate to think that there's some straightforward correlation between track errors and intensity errors. You know, and I'm not sure how one would go about quantifying it. It would be nice to do the kind of perfect model experiments I described, but with an actually good model like HFIP or something like that. And so where you can control things like the environment that the storm is in.
Actually, Kerry, thanks. Excellent talk. I would like to follow up with what you said, and we have noticed this in the beginning when we started developing the HFIP system. One of the terms that we were playing around at that time was the horizontal diffusion term. Long-term forecast, even within what you said, with the landfall, even without the landfall, long-term, there were environments in which there were changes to the environments in which it was really performing to a way in which long-term errors were really affected by track errors as well. So it's pretty consistent, although we couldn't quantify it at that time, and I don't know a way we can do it, and it looks pretty, it makes a lot of sense there.
Yeah. Sure, and you know, I think again the main message here is that it's obvious, I suppose. Intensity is not independent of track, and more quantitatively, at longer lead times, it's the track errors that seem to dominate the intensity errors, and so that's a good reason to try to develop different metrics. You'd like to be able to. I mean, what is it you're going to work hard to improve for society's sake, and sort of think about it from that standpoint.
So yeah, I think moving on, James had a few questions probably because he's in the forecast front. Probably he would like to share something so that we can initiate some discussions, I thought.
Sure. I just, you know, the idea of moving away from, which was the phrase Kerry used more than once, the storm-centric metrics. I mean, I think you have to remember that there are plenty of applications for which local probabilities are unimportant. I'm not saying they're always unimportant, but if you are a state-level emergency manager and a category 5 storm is forecast to come to the Texas coast, the local probabilities of those impacts, of course, are going to be tiny at any particular point that you choose. Yet, it's very likely that somebody is going to experience category 5 conditions, and communities need to be prepared for that. So when you are a emergency manager on anything other than a city, you care about the accuracy of those storm-centric forecasts. And so I think the point is that different users have different needs. Many individuals are rightly interested only in what the odds are for them, but there are plenty of users for which storm-centric metrics are very, very important still.
Okay, James, the only thing I might add to what you said is, and my point is well taken, obviously, but if the person that you're talking, the hypothetical person you're talking about, had access to all the probabilities in Texas, not just one point, but the grid of probabilities, like you actually display at NHC, the grid of probabilities, those would presumably be useful because they are a good indication of where the storm is likely to come ashore and so forth.
Right, that's true. That's true. But 36 hours in advance, that person is not going to know whether it's going to be Corpus Christi or somewhere else, and therefore they need to know whether the NHC's forecast of a Category 5 landfall, irrespective of which city gets struck, is very important to their level of preparation, because large areas need to be evacuated, and it makes a difference whether they can count on a Category 5 coming ashore or whether it might well be a Category 2. And
Right.
so their decisions will depend in large measure on the storm-centric qualities of the forecast.
So if I had a map in your case of exceedance probabilities for the Cat 5 threshold, whatever that is, I've forgotten, for Texas at 72, 120 hours and so forth, why wouldn't that be just what that person needs? In other words, the person doesn't need to know where the center of the storm is, I would argue, for the first place, because the worst conditions might not be near the center or might be off on one side.
Well, in a Category 5, they're going to be pretty darn near the center.
Okay, they may be, but that's sort of incidental. If I had a map, if I were such a planner and I had a map of the probabilities of exceeding Cat 5 winds in Texas as a function of lead time, why wouldn't I be happy with that?
You probably would like that, but they're going to be small everywhere, for one thing. And what I'm getting at is that if NHC, if the EM knew that a Category 5 forecast 48 hours from NHC was highly reliable, that there was a very strong chance that an actual Category 5 storm would come ashore. And you measure that, of course, by the storm-centric error, then I think that EM acts differently than if the storm-centric intensity verification is so poor that they don't have confidence that a Category 5 storm is going to come ashore, and they respond differently. And so I think in that case, where it comes ashore and in which city, in terms of the kinds of decisions they make, whether or not to evacuate, not where, but whether, let's put it that way, I think depends more on the quality of the storm forecast than it does on the specific local forecast. Certain decisions depend on different attributes of the forecast.
Yeah, I get that, James. But so, I mean, one thing you could do, right, is accumulate all the pointwise probabilities along in Texas. And that would give you the overall probability of a Cat 5 strike somewhere in Texas. And then, so that's important. I agree with you that that's important information to that person. They can't look at a map of probabilities that are numerically very small because they're at points and say, oh, gee, you know, do I have to worry about a Cat 5 or not? But if you accumulated them along in the all of Texas for that lead time, it would give you the overall probability of having a Cat 5 somewhere in Texas. Then you could look at the map of that distribution, right, to gauge where it's most likely to come ashore. Then the question really is, are those probabilities any good? I mean, this is the whole thing is you have to have a long record of having made such forecasts and verified them in a probabilistic set using probabilistic metrics like reliability to tell you whether you're any good at making probabilistic forecasts. But I guess my feeling is you can take all those pointwise probabilities and sum them, right? I still don't get why it should matter where the center of the storm is coming ashore as an additional piece of information to that. I just don't get that, but
well,
you know, I'm obviously happy to be persuaded.
No, I don't think that was the point I was trying to make, because at the time you have to evacuate people, you don't know where the center is going to come ashore. You don't have time to wait for that. So
no.
you are making your decision about whether to evacuate a big chunk of the coast based on what kind of storm you expect to come ashore, not necessarily exactly where. And so in that case, you care about the quality of the particular deterministic forecast that's being made. And the ensembles don't give you that. NHC doesn't make a whole bunch of forecasts except, you know, yes, there's the climatological wind speed probabilities, but there is an actual track forecast and there is an actual intensity forecast that folks are going to use, and so they're going to care about how good it's going to be. There are just a variety of applications. That's the only point I'm going to make, and that point probabilities don't address every question that an EM or a user is likely to have. I would argue.
Okay, but James, you still need to persuade me of that point, and
okay.
Maybe we should do it offline. I'm trying to be open-minded about it, but yeah, I still need to be persuaded of that. Now, of course, one point is if the ensemble forecast, each one of them, is inferior to what you're calling a deterministic forecast, as is the case with the global ensembles, that's a very different matter. There, of course, that's the only choice. I would absolutely argue in favor of a deterministic forecast. But we're trying to move in a direction where we basically have the best of both worlds. We have a large ensemble, any member of which is as good as any other, or what you're calling deterministic. We're not there yet. That's true.
In the interest of time, Kerry, there was another aspect that Kerry had mentioned about RI. I think we need to initiate some discussions on RI. Do we? Because the whole HFIP, one of the major goals of HFIP is to improve RI forecast as well. So is there any discussions, because Kerry wanted to initiate such discussions too. Is there any discussions from anyone on why they strongly feel that the numbers threshold is important? Or, as Kerry said, is it spectrum, we don't need to care about it?
Hey, Gopal, this is Mark.
Yes.
I have a comment on that. Can I jump in?
Sure.
Okay. Two things about that. When you look at the overall distribution of the intensity changes, yeah, you really don't see some kind of secondary maximum in the PDF for RI. But one part of that I don't think that diagram takes into account is that those intensification rates occur episodically. So you have not much intensification. There's a certain set of physical processes associated with eye formation, contraction before you're too close to your MPI, where there's a certain set of physical processes that cause a jump in the intensification rate, and that is RI. And I think that's a real thing. That I think the processes that are going on during that 24-hour period, typically when the max winds intensify, has a physical reasoning behind it. And the second thing is that there really is a practical importance to it. That was kind of the original motivation, that there are these cases where you increase by 2 Saffir-Simpson wind categories before landfall, and that has all kinds of practical implications. And that's where the original definition came from. But I do think there's a physical component too, if you take into account the time distribution within a storm.
Yeah. Continuing on Mark, that was my question too, because from the impact point of view, that as Mark said, if you're going to intensify a storm versus slowly intensify a storm, there are differences both in terms of impact as well as the physical processes, isn't it?
Yeah, I certainly don't want to be misconstrued as saying that it's not important to forecast intensification rates, because that would be crazy. Of course, it's important to forecast that. I guess I'm against the threshold idea. There's some magic number, and when it's more than that, it gets put into different bins in the public's mind and our minds, maybe in the way we make decisions. That's what I'm not too comfortable with, I guess. But Mark, to your point, yeah, obviously we have to forecast intensification.
I think.
Yeah.
Yeah, I was just going to say that the same goes for the second category.
So, I'm sorry, somebody, whoever spoke, got cut out just now.
Probably Mark.
Yeah, sorry. Yeah, I was just saying that same issue. Yeah. I was just saying the same issue with Saffir-Simpson wind categories. There's a 5-knot difference between a category 2 and a 3, and yet if you characterize things in terms of categories, everybody makes a big deal about a major hurricane. And so, yeah, if you have this magic 30 knots in 24 hours as being the only thing, then yeah, that is a difficulty.
Well, I think there's another point here, Kerry, and that's that in an idealized sense, almost every storm goes through RI right away and goes up to MPI. If you have the right conditions, they do RI. And so what really happens in nature is, why doesn't it do that? What is preventing that from happening all the time?
We seem to be on top of the hour. There are two other questions in the chat. Kerry, will you be staying a little longer? And if folks want to say,
I can stay longer. Yep, I can stay longer. Sure.
So there is a question from Gregory Patrick. Are you still there?
Yeah, but you're muted.
Yeah. So ask question. You're muted.
Yeah, I believe my question's already been discussed. Thank you.
I have a hello. Can you hear me?
Hey, Pablo.
It's Pablo. I have a comment. Well, is it really coming? Earlier was alluded to about what do the EM needs, the emergency manager. My experience over the years is, when it comes to explaining probabilities, it's really understanding the frame of reference. You understanding if what you're using is a point probability, an area-based probability, and then properly applying that to whatever need they have. I can tell you from the years of working with the county EM managers and the state level EM managers, often in times, they want to know more than say, what is the probability Miami is going to say hurricane force wind? What they really mean is, what is the probability Miami-Dade County is going to say hurricane force wind? That's a different question, right? And therefore, now you have to transition from a point-based probability to an area-based probability. Well, the same can be said of the state of Florida, asking what is the probability the state of Florida is going to see hurricane force wind. Those are different questions, different frame of references, right? And I think the more agile we can be in terms of the data available to us, data mine, and get the right information to answer those different types of questions, the better we're going to be able to target the needs and questions that we often face.
Yeah, absolutely. Totally agree with that, of course. And maybe it would be nice to envision a user interrogated system where whoever needs to know goes into a website or something and says this is defines the area in which they want to know the probabilities, for example. But yeah, absolutely.
Yes. And Kerry, let's thank Kerry once again in the interest of time. And we hope that you can join such meetings once in a while. And thank you so much, Kerry.
Thank you very much. Nice to see you all. And thank you for your great questions, too.
Sure.
Terrific. Yeah.
And thank you, everyone, for joining. Thank you. Thank you, Kerry.
Thank you.